Now we are. Okay, now we're recording. So we're going to start with a left-hand limit as you see the chart on the left side. So this is going to be for the left-hand limit. And whenever we are taking a limit from the left side, this means you are approaching that number from the left, basically from the left of the x-axis. So here's 2. This is the number we are approaching, and we are approaching it from the left side, meaning we get to use all these numbers and get extremely close to the value of 2. But based on our domain, can we actually touch 2? No. All right, good. So that's what we're going to do right now. So I'm going to pick numbers to the left of 2. And I'm going to keep it simple. I'm not going to use anything over here. That's going to be too negative. I'm going to start at 0. I'm going to say, okay, let's start at 0. And then let's move up to 1. And now I want to get numbers really, really, really close to 2. So let me go 1.5, 1.7, 1.9. Whoa. And then how about 1.99? And then how about 1.999? The more 9s you add, the better results you're going to get of where your limit is headed. So let's add a 4th 9 in there since we have the room. And then I'm going to put a 2 there. So let's see what these values give us when we plug them in. And like I said, I'll dual wield. I'll use Desmos at the same time. Don't break my computer. Let's see.
Dual wield.
Dual wield.
Nerd.
Like Halo, right? All right. So I'm going to use Desmos. This is Desmos on the left. And I'm going to type in the exact function we're analyzing. X squared plus 2. And what's great about Desmos is it can make an XY chart for you as well. So I'm going to do that. I'm going to hit this little gear icon above. And you see that little XY chart it has? Go ahead and click on that. And now I'm just going to fill out the chart to the right. So I'm going to type in the same numbers we have here. 0, 1, 1.5, 1.7, 1.9, 1.99, 999, 1.9999, and 2. All right, so let's just go ahead and fill in this chart on the right. So 2, 3, 4.25, 4.89, 5.61, 5.96, 5.996, and then 5.9996. And then we see that as X starts getting closer and closer and closer to 2, we see that my Y values are getting closer and closer and closer to what number?
6.
6. Good. I'll say that one more time just so you get it. So as X approaches 2 from the left, so as X gets closer and closer and closer to 2, we see that Y is getting closer and closer and closer to what number again?
6.
6. Good. But can we actually land on 6?
No.
Does this domain restriction let us land on 6?
No.
No. Good. Therefore, we have to claim that this point is going to be undefined. That's only by that domain restriction above, though. Okay. So let's go back here. So we're going to say that this point is undefined. Okay. And now, just to go over everything you have just done and put it into an actual limit notation, we're going to say the limit as x approaches 2 from the left side. So you see the little minus sign notation I put, that minus sign goes, it goes above the 2. So it says, what that notation means is that you are approaching 2 from the left. So we're going to say the limit as x approaches 2 from the left of the function x squared plus 2 will equal, and just like we did on the chart above, as x approached 2 from the left, my y values got closer and closer to what number?
6.
6.
There you go. And that is a left-hand limit. So now we know the limit from the left is 6. But some things should start turning in your mind. How can a point be undefined, but a limit exists at 6? So this is getting us into the informal definition of a limit. So your brain should be rolling right now. A point can be undefined, but a limit can still exist. It's mind-blowing, I know. Okay. So if there's a left-hand limit, then there's definitely a right-hand limit. And if we do limits from the right, well, what that means is that the number we're approaching, we come from the right side of the x-axis. So we're coming this way, which means if you approach a limit from the right, all the numbers are bigger than the number that you were approaching. So we're coming from positive infinity to get closer and closer to this number. So limits from the right approach from the right side, where all the numbers are bigger, which means let's go ahead and choose numbers for my XY chart. Let's choose numbers to the right of 2. And I'm not going to get crazy, just choose some. So let's start with 4. Let's start with 3. And then let's go to, where are we? Oops. Let's go to 2.5. How about 2.2, 2.1, and then let's add some zeros in there. 2.01, 2.001, and how about we end on 2.0001, and I'll stop on 2 there. And again, look at the Desmos. We'll type in the same numbers that we have in this XY chart. So we'll do that here. 4, 3, 2.5, 2.2, 2.1, 2.01, 2.001, and 2.0001. All right, and I'll fill in this graph or this chart. 18, 11, 8.25, 6.84, 6.41, 6.04, 6.004, and 6.0004. And of course, when we get on 2, we land on 6. Okay, so just like the left-hand limit, we see that as my x values get closer and closer to 2, once again, we see that my y values are getting closer and closer again to what number?
6.
6. Good. So this means that as x approaches 2 from the right side, we get that our y value, our limit, is going to be 6. But once again, can this point actually be defined?
No.
No. Only because of that domain restriction again, right there. X cannot equal 2. Okay. And now, let's go ahead and write notation for the right-hand limit. We're going to say the limit as x approaches 2 from the right of the function x squared plus 2 will equal 6. Okay. And now you guys are about to prove the existence of a limit, or we will prove the existence of a limit with your help, right? So as x approached 2 from the left, the limit was 6. As x approached 2 from the right, the limit was 6. So for a limit to exist, the left-hand limit and the right-hand limit must be equal. So are these limits equivalent to each other?
Yes.
Yes. Again, the left-hand limit 6, the right-hand limit is 6. This means if the left and right are both equal, this means that the limit from both sides at 2 will exist. So to put that in writing, we're going to say, it's a good color. There we go. The limit as x approaches 2 from both sides. So this time, there's no plus or minus anywhere. So if you ever just see the number as x approaches a number, it's asking you to approach the limit from both sides. So what we're going to say is the limit as x approaches 2 from both sides of the function x squared plus 2 is also equal to 6. And this is only because the left-hand limit is 6 and the right-hand limit is 6. Therefore, our limit exists. And there you go, guys. That is as informal as you're going to get for the definition of a limit. I guess I should draw this graph. So one moment. I'll just do a sketch. So we come down. We're at 2. So we look like this. And then here, you'll have an open circle and take off. 1, 2, 3, 4, 5, 6. Hey, I got it right in the money. So what we did was, as we approached 2, as we approached 2 from the left, we saw that y got closer and closer to 6. And then as we approached 2 from the right, as we approached 2 from the right, we also saw that y was getting closer and closer to 6. Therefore, the limit from both sides has to be 6. But again, if your curious mind is going crazy, how can a limit exist at a point that's not defined? Well, we will get into that later when we start learning something called continuity. Today, we just learned about the informal definition of a limit. What does a limit do? How do you read a limit? How do you apply a limit? Like, what is going on with all this? And again, if you can keep it as simple as possible, as x approaches a number, all we are worried about is the behavior of y. What is y doing? What number is y approaching? That's what the limit wants. So down below, the informal definition of a limit. Suppose f of x is defined when x is near the number a. This means that if f is defined on some open interval that contains a except a itself, then we write the limit as x approaches a of f of x equals some number L. So that may sound complicated, but it's everything we just did above. So basically what we were saying is that as we approach 2 from the left and the right, this was the number that x is getting really close to, but x can never touch, only because of that domain restriction. So as x approached 2 from the left and the right, we got that that limit was going to equal 6. And like I said, the in English translation down there, if f of x equals some number L, as x approaches some number a from both sides of the x-axis. So basically, on our limit above, y equals 6 as x approached 2 from the left and the right. And that's your informal definition of a limit. Any questions on this page?
Couldn't you just plug in 2 and you'll get 6?
But can we?
That's
That's the question. Why can't I plug in 2?
Yeah, why can't you? I'm curious.
Look at the very first sentence.
Because x can't
Because
equal
it told you
2.
it can't.
Because we can't equal 2. So therefore, we just can't plug in 2. Sometimes we wish it was that simple, but it's not. Yes, we know if you plug in 2 it's 6, but the point of a limit is, hey, this point's undefined, but the limit can still exist. So does that make sense? Because we're going to come across a lot more complicated limits where we just can't say, hey, plug in that number and it's going to work. So that is a good thought to have once we start getting further into limits. If you want to see if a limit works, yes, plug in the number right away. That is one great rule for solving limits. But this one, we can't plug into because that domain restriction says we can choose any number we want except for 2. And that was the purpose of the exercise, to show you that, hey, even if a point's undefined, as x approaches that number, y, we can still have a limit depending on the behavior of y. So that's everything that's going on. Any questions on that? Everybody feel good?
No, for the epsilon delta definition.
Oh God, no. Erase that out that. Erase it. Okay, cool. So guess we'll move on. Everybody's good. Okay. This next page is nothing but definition. It's going over everything we just did on the last page. So first up is the left-hand limit. We already did a left-hand limit. So what does that mean? So the left-hand limit, this notation is read as the limit of f of x as x approaches a from the left. This means as x approaches a, all the values of x are less than a. This makes sense because that's everything we did above. We were approaching 2, and if you approach 2 from the left, all of these values are smaller than 2, right? All of those values, I missed one, but yeah, all of those values are smaller than 2. So this is what it means to approach a number from the left. All the numbers are smaller than the number you are approaching. And then what else does it say? So L is the limit from the left, or the left-hand limit, if f of x is close to the limit, or to L, whenever x is close to a, but to the left of a. So basically, we approached 2 from the left, and as x got closer to 2, we saw that y was getting closer to 6. And then right-hand limit. We did the right-hand limit already. So read as the limit of f of x as x approaches a from the right means that as x approaches a, all the values of x are greater than a. And again, everything we did already. So once again, we approach 2 from the right side, meaning all these numbers were bigger than 2. So that's what it means to approach 2 from the right. So based on the definition, as we approach 2 from the right, we saw our y values getting closer and closer and closer to 6. And that's your right-hand limit. And then the last one is, well, the existence of a limit. For a two-sided limit to exist, the limit from the left and the limit from the right must exist and be equal. So that's what we did above on the last page. So this says the limit as x approaches a from both sides. So if there's no direction specified, this means it's a two-sided limit. This means you're approaching the limit from both sides. So we say the limit as x approaches a of f of x equals L if and only if the limit from the left at a equals L and the limit from the right at a equals L. And if the left hand and the right hand are equal, then we have a limit that exists. Same thing we did up there. Our left hand limit was 6. Our right hand limit was 6. Therefore, the limit from both sides must also be 6. All that definition there. Any questions on that? So that was just definition on everything we covered on the first page. we were doing left-hand limits and right-hand limits before you even knew about it. So there you go. Okay. So next, on this page, I want you guys to go ahead and practice putting these functions into your calculator, practice putting these functions into Desmos, and practice picking numbers. If you're wondering how do you pick numbers, well, this limit says it wants to approach 1 from both sides. So there's two XY charts here. You're going to have the left-hand limit and a right-hand limit. Choose numbers to the left of 1. As long as the number is to the left of 1, you're making great choices. But again, the closer you get to that X value, the more information you are going to get. So I'll give you guys about 5 to 10 minutes to work on these limits and let me know what you get. If you need help typing them in your calculator, I'll show you how to write them, type them in your calculator, depending on the model, anything like that. So go ahead and practice filling out this chart. Use Desmos if you need to.
Can you show us how to type them into the calculator?
Sure. Which one are you using?
I have the TI 30XS.
Okay, so this blue one, right?
Yeah.
Okay, so fair enough. I mean, I'm just going to write it on here. So if you're going to type, because remember that the TI 30 and the TI 84s have the table feature, right? Where you can make an XY chart on it.
Yeah.
Which will
I
help you out a
just
lot.
found it.
Yeah. So for your TI 30XS, let me see. I'm going to zoom that. I'll do some calculator instructions over here. Oops. Undo. There we go. So for a TI 30XS, you are going to click on table. And then after you hit table, a Y equals screen is going to pop up. And if you're going to type in this fraction, well, lucky for you on the TI 30XS, there is a button that says N over D. If you type in N over D, it's going to make a fraction for you. So it'll be perfect setup for you. Did you find the N over D button?
Yes.
It's right above the sign button.
Found it.
Okay. And now it's going to give you two boxes, right?
Yes.
So you're going to type in the function just as you see it. You're going to do x minus 1 over x squared minus 1. So N over D button gets you there. Okay. And then after you type that in, let me do it with you. X minus 1 over x squared minus 1. You're going to come to a screen that says start, step, auto, ask. So ignore start and step and go straight to highlight ask X.
Okay.
Highlight that, hit enter, 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 and then you're going to get an XY chart. If it's not blank, just hit the delete buttons and it'll clear out the screen for you on the values that are there. And start typing in the values you want that are close to, oops, my calculator froze. And then 4, you'll come to a blank XY chart and pick the numbers you want. So we're getting closer to 1. I would say start with 0 and then probably go 0.5, 0.7, until you get close to 1. And the TI-30 only does 3 inputs at a time. So all you have to do is go back up with the little D-pad there and just overwrite it and hit enter if you want more values. Cool?
Awesome.
Got it?
Yep. Easy enough. Thank you.
All right. If you're using TI-84, 83 or above, I'll say 83 or above. See if I remember this. 1, you'll hit the y equals button. 2, you might have to do classic input, or if you find the fraction button on your calculator, great. If not, classic input is going to be x minus 1 divide x squared minus 1. And then after you do that, 3, you're going to hit second and then find the window button. So hit second window. 4, you're going to come to a, what is it? Start, step, change
Yeah.
table, I think.
Yeah.
Is there a start on there?
I think it's a start and step.
I think it's start table and I think change table.
Oh, yeah.
So you'll just ignore those for now. And then you'll see independent. And then you'll see auto and ask. And I think it's ask X, maybe. Highlight that, hit enter. Step 5, you'll hit second, and then you'll hit graph. And you'll get your blank X, Y chart. And again, if there's numbers there, just delete them. And those are your calculator instructions. If you're using Desmos, well, your life is easy. Look at this. You just go to Desmos, you type in the function. I'll do that. I'll say x minus 1 over x squared minus 1. And then after you hit that, I just hit the gear button, hit the table button, and bam, there's my XY chart. And I can start picking numbers for the left limit and the right limit, like 0.5, 0.7, 0.9, stuff like that. All right. So try number 1 out. And if you got number 1, see if you know how to type number 2 in the calculator. You might have to, you'll definitely have to replace all the T's with X's on number 2. Any questions so far? What we got next? Cool. I'll let you do this page, Ryan. Down for it.
Wait, what? What am I doing?
You want to do this page?
Sure.
Cool.
Let's see.
Guess you'll share your screen. What are you using? Your calculator at home?
Me?
Yeah.
Yeah, that calculator you gave me like 2 years ago.
The chromed out one?
Yeah.
Yeah, it's a good one. There's like
Yeah.
there's like 6 more at school that we can't get to. But there's no need to when you have Desmos.
No.
Yeah.
Desmos is the best.
All right. Let me know when you're ready. You can share your screen.
Well, I got it. I'm all over it.
Oh, snap. Hey, I wrote
Let's
that.
see. Yeah. You said, what was it? This one, right?
No, number 1. Go back up. So you'll, oh God. There you
This
go.
one? Okay.
Yeah, number 1 and number 2 if you want it.
Okay.
But, I mean, I guess we'll give them a couple of minutes to see if they can get it.
All
So
right.
can we use Desmos on a test later on?
Yeah, I said you can use Desmos. If I'm showing you how to use it, then you should be able to, then you'll be able to use it on a test. Just remember that you still have to show all your work.
Right. Y equals. All right. Oh, I can't even write on this. What?
You should be able to.
Let's see. Draw.
Oh, but it's not your format, right?
Yeah, it's fine.
I wonder if I can send you the link for that format. We'll try it later.
Hopefully that's legible.
Yeah.
And 0.999. Do a little ellipses.
99999.
Yeah.
Yeah.
I probably should just download the original PDF. 526. So 3.
On the second question, is the -3 outside of
Yes.
the,
Mhm.
okay, thank you.
The -3 is outside. Good.
And it's divided by t squared as the limit approaches 0.
Yes.
All right. Next one. Ew. I swear my handwriting isn't that bad.
Is it because of the program or what?
I think it's like it's because I'm writing on it using Zoom maybe. And Zoom just sucks.
Mm. Wait. I know you're good. Like that's not annotate, right? No.
No, yeah, I'm like writing using the share screen, I guess.
Yeah.
Boxes are too small, bro. Get rid of
Zoom in.
boxes.
Zoom in.
No, I
Oh
can't.
God.
It's not
Oh
letting me.
wow. What was that?
Woo. Woo. Let's see. 0.49. 9. 8. 9.
All right.
And they're working on 2 as well, right?
2, but I guess we could talk about 1, or should
Sure.
we talk about them after we finish all of them?
I mean,
We'll talk about 1
yeah,
Yeah.
I think they get the idea from
as we
just
go.
1.
Okay. You guys see Ryan's numbers? Did everybody come out with, or actually, let me ask, what do you guys think the limit was for number 1?
0.5.
0.5. Good. Because you see your limit from the left is getting closer to 0.5. Your limit from the right is getting closer to 0.5. Therefore, the limit from both sides has to be 0.5. So any questions about that? Any calculator issues? Anything at all? We got a thumbs up. Cool.
Yeah.
Yeah. Okay. Before moving on to number 2, or before Ryan moves on to number 2, Does anybody know of another way to solve this?
Ooh, sub me in, coach.
Hey, tag in. Boom. So today is all about learning how to use your calculator, learning how to pick a number, and just learning about limits. Well, in the next section, we're going to get into algebraically manipulating limits, where we don't have to use a calculator unless we need to. So what is another way to solve this, Ryan?
I notice in my denominator that is a difference of squares. So I can factor that denominator as x minus 1 times x plus 1. And then now that I have x minus 1 factored from the denominator, that means I get to reduce. Now I'm just left with 1 over x plus 1. And then now that I have simplified my limit, I can evaluate that limit by just plugging in the value that x is approaching. So if I plug a 1 in for x, I'll get 1/2.
Yeah, which is our limit. Woohoo. Did anybody try to plug 1 in from the beginning? If so, what happened?
You get an error.
You get an error in your calculator?
Yeah, my calculator gave me an error.
All right, cool. Well, let's go ahead and explore what happens if you plug in 1, Ryan.
Sure. So
the
if I
beginning.
evaluated this original limit as it was by, again, just plugging in 1 for x, you'll get the limit as x approaches 1 of 1 minus 1 over, and then 1 squared is 1. So we'll have 1 minus 1 in our denominator. And this would be 0 over 0.
Does anybody know what 0 over 0 is?
Fine.
Not undefined. We have a new word for you in calculus.
Indeterminate.
Good. So if you ever end up with an indeterminate form such as 0 over 0, this means that you have to go back and fix it. And when I say fix it, you fix it algebraically or you use your calculator. Again, today is all about using the calculator, but just know there are other ways to solve limits algebraically.
Right. And what's really helpful about plugging in the number first is, in this case, we learned it was an indeterminate form. And this special type of indeterminate form actually tells you how you need to solve this limit. And these 0 over 0 limits are solved by factoring and reducing for the most part.
Yay. All right.
Yeah.
All right. Everybody good with number 1?
Yes.
Let's see if it lets me scroll. Oh, wow. What is it doing?
There you
Good
go.
God.
Oh, man. Not good.
Oh, no. I have to use like the little...
Let me see. Let me see something. Maybe I'll send you the other link because you like using the other version.
No, this is fine. It's just like, for whatever reason, the interface is kind of weird. All right. We're good, I think.
Sure.
Hold on. Scrolled up a little bit. Yeah, we're good. Ooh, this one looks spoopy.
I'll let you fill that out. I'll send you the link for the other format of OneNote just in case it's better.
Okay, sweet. Then if all else fails, I'll just put the PDF on mine.
Yeah, and then we'll figure it out. We'll mash them together.
Yeah.
Or they just have to watch the video to get it. Yeah.
Let's see. What's the original function? Ooh, okay. Root of. All divided by x squared.
Uh-oh.
Hmm.
Where'd you go?
Oh no, I was plugging into the does most thing. I'll scroll back down. Ooh. Stop. Stop.
Goodness. Malfunction.
Yep. Okay, there we go. All right. Oof, this is a weird one. One more zero. Right. 20. Oops. I forgot I left Skip on the patio.
Nice.
He's just like pawing vigorously on my door.
Let
doesn't-
me in.
He doesn't weather the elements well.
Mm.
What just happened?
You got you move screens.
Bada bing.
Okay, cool. So for number 2, did everybody get, of course, if you round up, I think you can leave it as 0.0167 or even 0.17, but did everybody get 0.17?
Yes.
Got a yes. Got a thumbs up. I got 2 out of 20.
Yes.
Crushing it.
Yeah. All right, 4. Okay. So again, it's just practicing typing this into your calculator, knowing what points to pick. You see that as Ryan was getting closer to 0, he picked 0.1, 0.01, 0.001, 0.0001. So honestly, the more zeros you put into getting closer to a number, the more accurate you're going to be on your limit. So, and again, if we were to solve this algebraically, which we're not going to do right now, going to take some time, since there's a radical in the numerator, we would actually multiply this one by the conjugate to help simplify it. Okay. So, any questions on this before moving on?
So sorry, I'm just having a lot of issues with the stupid calculator and the Desmos thing. Like, I get the concept and I'm following along. I just can't do it here at my desk. Is there any way you can show us real quick on Desmos how to make a little table and put the
Sure.
information in?
Yeah. Let me do that. All right.
All over it. I'll beat you to it.
No.
Yeah.
You can do it?
Yeah. I'm already
Okay.
sharing. Why not?
Okay.
Okay. All right. So in this case, we have to input our function, which was root of x. So even though it's a t, you can just use any arbitrary variable. So in this case, I'm just going to use x.
How do you get the square root symbol?
Oh, okay. So when you're typing it, SQRT, and it'll pop up.
And there might even be a option in that little keyboard menu you see in the bottom left
Right. So
corner.
if you go down here.
If you go to, yeah, right there, right next to pi.
Boom.
Yeah, that'll get you there too.
So then x squared plus 9. And then you need to make sure that you move your cursor outside of the square root. You can tell because if I try adding that -3, do you see how the square root extends? But if I move outside of the square root, that root no longer is extended. That means this -3 is outside of that radical.
Yeah. Before you put the -3 though, hit the division symbol to make it a fraction.
So check this out. If you highlight everything and you hit division, where is it? There it is. Nope.
Oh, no.
Oh, it's because I switched off my desktop. Damn.
Don't lie to me.
Well, that's how I do it on my desktop. Don't tell me what to do.
All right. I want to see this magic.
Trying to find it. Oh, there it is. There it is. Yeah. So
nice.
if you hit the /, it's right next to the shift button.
It'll make
So
it
again-
a fraction. Cool.
Right. If you highlight the entire numerator, hit the /, and then it'll turn it into a fraction.
There
Right.
you go. And then
Now you go to the edit list, and there's this little matrix box here. It'll convert it into a table for you. And use 0.1, 0.01, 0.001, 0.001, 0.0001.
all right. Excellent. Does that help you out?
Yes, thank you so much.
Excellent. Yeah, so just be careful how you input them on your calculator. Make sure you have parentheses where you need them to be, and make sure it looks exactly like the expression you're taking the limit of. Okay. Everybody good to move on?
Yes.
Yes. Okay. I'll jump back in then.
Oh no, yeah. Oh no. Oh,
My
no.
turn.
Oh no.
Boom. 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 It's like the same screens.
Stop copying me, bro.
I know. Okay. So the next limit we're looking at is a trigonometric limit. Yay, they are back to haunt you from your worst nightmares, okay? All right. So this is going to be one of the most important trig limits that we will use basically all semester. So when you're typing in trig limits, one thing is very, very important. You need to put your calculator in radian mode. So before you even start punching numbers in, make sure to put your calculator in radians. Calculator in radians. And Desmos, I believe, already starts off in radians. If you get that little wrench that you see there in the top corner, look at the very bottom. It's got radians and degrees. So it's always in radians. Okay, so not to spend more time on this, let's just go ahead and pick numbers to the left of 0, to the right of 0. So here's left, there's right, and if I'm picking numbers to the left of 0, again, we have negative 0.1, negative 0.01, negative 0.001, and how about negative 0.0001? And if you feel that you want to put more zeros, go ahead. Again, the more zeros you put, the more information you're going to get. And I'm going to use the same values on the other chart, 0.1, 0.01, 0.001, and 0.0001. And let's see what this gives us. So guess I should type in the function first, right? So let's see. Just have sine of x over x. There we go. And then I hit the little gear icon, table. There we go. And I'll just use the numbers I've written. Negative 0.1, negative 0.01, negative 0.001, and then negative 0.0001. And look at my values for y. So over here, I just have 0.998, 0.999, and again, 0.999. And this one even spewed out 1. So again, as you can see from the right-hand limit, as my x values get closer and closer to 0 from the left side, we see that my y values are going to get closer and closer to what number? Anybody?
1.
1.
Yeah.
Thank you. So we get closer to 1. And the same for the values on the right table. You'll get the same exact things. 0.998, 0.999, 0.999 again, and eventually we get to 1. So this means since the limit from the left is 1, the limit from the right is 1, the limit from both sides of this trig limit is going to be 1. As you can see, of course, from the pictures on the right. So let me just write this out. The limit as x approaches 0 of sine x over x is 1. So what you should do with this trig limit, it's actually, we can call it a trig limit identity. Whenever you see the limit as x approaches 0 of sine x over x, as long as x is approaching 0, the answer is always going to be 1. This is going to be very important on the next lecture. So star this, save that somewhere. If you're in your room, right on your wall. And
Do that all the time.
yeah. So as you see from the graph on the right, as we approach 0 from the left, y got closer to 1. As you approach 0 from the right, as you approach 0 from the right, y again gets closer to 1. So therefore, the limit as x approaches 0 of sine x over x will be 1. All right, and to be nice, here's some other trig limits. So this also can be said for the limit as x approaches 0 of x over sine x is also 1. And this can also be said for the limit as x approaches 0 of tangent x over x is also 1. So these are good to know as well. And then the same could be said for tangent. The limit as x approaches 0 of x over tangent x is also 1. So just look for those trig limits when we get to the next section. For now, just know them. Okay, and make sure when computing these, your calculator is in radians. All right, all good? Where'd my chat screen go? There we go. Okay. Let's see. I think the last limit calculation problem. Yes, we're almost there. Okay. So for this one, I do not recommend putting in your graphing calculator. You might break it because as you see here on the graph, it says there's a number of infinite wiggles and it may take your calculator forever to graph it. So just do an XY chart to be safe, or just watch what happens and write what I have down. So we are looking at sine of pi over x. Oh yeah, I'll do that. I'll put it on my computer. Let's see if I can break mine. Okay, sine of pi over x, and we're approaching 0 from both sides again. So we want to get it extremely close to 0. But for this one, it's a little tricky, the numbers you pick. So I've done it for us already. So here are the numbers I'm picking. Here's my XY chart. So it seems that 0.09, 0.07, 0.06, 0.03, and 0.01 are the only numbers that give me the results that I'm looking for. So these are the numbers I'm going to use for the left side and right side. So here for the left-hand limit, I'm using negative 0.09, negative 0.07, negative 0.06, 0.03, and negative 0.01. And then same numbers on the right limit. 0.09, 0.07, 0.06, 0.03, and 0.01. Okay, so looking at our XY chart over there on Desmos, I get 0.34, negative 0.78, negative 0.866, and then positive 0.866, and then 0. And then the next one, I think all the signs are just reversed, right? Yep. 0.78, 0.866, negative 0.866, and 0. Okay. So let's look at our XY charts. So look at the left-hand limit. So as my values on the left side get closer and closer to 0, what value is my limit approaching, or what behavior is my limit showing? Because by the numbers, it looks like we're going to hit what?
0.
But can we hit 0?
No.
No, because that says pi over x. And if x is in the denominator, what number can x never be?
0.
0. So therefore, can this point actually be defined? So I guess what I really want you to do is look at the behavior of your numbers. Look at your y values on the left-hand limit and look at your y values on the right-hand limit. What are they doing?
They're going up and down.
Good. They're going up and down, right? So on the left hand, you're at positive, and the right hand, you're negative. And every time you get closer to 0, they're doing this, right? They're going up and down, positive, negative, positive, negative, positive, negative. Will they ever meet?
No.
No, because can they ever hit 0?
No.
No. So as they get closer and closer and closer to 0, they're just going to keep oscillating up and down, positive, negative, positive, negative, positive, negative, which means that is there a limit from the left and is there a limit from the right?
No.
No. Since there's no limit from the right and there's no limit from the left, this means, in the words of the great Lindsay Lohan, the limit from both sides at 0, what?
What?
Doesn't exist.
Does
What?
not exist.
What?
Thank
What?
you. You heard me. Mean Girls.
I feel like
Lindsay
I'm
Lohan
watching,
does math.
I feel like I'm watching your same YouTube video, but except I'm just in class.
It is, right? Same
It's literally
energy.
the same thing.
It's great, right?
I'm like leaving the room, but I still hear you.
There you go. So since we can't have a limit from the left and a limit from the right because they keep oscillating and will never meet, this means that the limit from both sides at 0 does not exist. Everybody good with that?
Yes.
Yes. All right. Good.
I was gonna say, well, whenever I just did the graph of this on my own, I was like, damn, this is like the most fun graph I've had been able to graph because I just scribbled everywhere.
it just keeps going up and down, right? If you keep zooming in on the infinite wiggles, I think it'll crash your computer and your graphing calculator. So don't do it.
Do it.
Do it.
Did it.
Do it.
Do it.
Okay, last problem. Basically, this one's important because it's teaching you how to actually read a limit and just understand the definition of a limit and how it exists. So we're just going to use this graph to answer the limit questions below. So let's start with the first one. The limit as x approaches 2 from the left of this function g of x. So all of this is g of x. So as we approach 2 from the left, what is our y value doing? What number is our y value getting close to?
3.
3. Good. So again, as you approach 2 from the left, we see that our y value gets closer and closer to 3. So this means the limit from the left is 3. Everybody good with that? Okay. And then let's do the one next to it. Now, as we approach 2 from the right side, we want to know what my y value is doing. So as we approach 2 from the right, what value is y getting close to?
1.
1. So the limit from the right is 1. Okay. Well, the last question builds off of these two answers. The last question says, what is the limit as x approaches 2 from both sides? And what's our answer?
Does not exist
Why?
because there is not a limit between both.
Because these limits are not equal, right? So for this problem, the left-hand limit was 3. The right-hand limit was 1. Does 3 equal 1? No. Yay, you guys are great. All right. Okay. And last set. As x approaches 5 from the left, as you approach 5 from the left, this means that y has to go here, drop down here, and keep going. So as we approach 5 from the left, y is getting closer and closer to what number?
2.
2. That's about 2, right? Okay, and then as you approach 5 from the right, y is getting closer and closer to what number?
5. Oh no.
Two.
Other
2.
way. 2. Good. So again, as x gets closer to 5 from the right, y is getting closer and closer to 2. So now, what is the answer for the last one?
2.
2.
2. Good. Because the left hand and the right hand limit are 2. They're both equal. Therefore, the limit from both sides is 2. All right. And that's how you read limits and graphs together. All right. So did anybody have a question about this guy? You're like, yeah, sure. All right. What if I said, what is g of 5? So
Say
basically,
1.
yeah, we'll say 1, right? It's around 1. Sure. Maybe a little above, but we'll say 1. So g of 5 is 1. Okay. So again, this should start intriguing your brain, getting your brain rolling, saying, okay, well, a limit exists, a point exists, but is this function continuous, right? So we have a limit that exists, that's a check. We have a point that is defined, that's a check. But in order for a function to be fully continuous, and again, we're not going to learn about continuity till 2 more sections, but in order for a function to be fully continuous, the limit value must equal the point value. And are these two values equal?
Yes.
No.
No.
Does 2 equal 1?
No. At all.
No. Therefore, it would be thrown out by the rules of continuity saying that this function is not continuous at x equals 5. But again, I'm just giving you stuff to think about. You don't have to worry
So
about it just yet. Go ahead.
So just to make sure I understand, so this is just for future reference. When you ask if it's continuous, we just pick
Exactly.
any point, test it out, and if it's not the same, then it doesn't work.
Exactly.
Okay. Got it.
There
Thanks.
you go. You're welcome. Okay, cool. And that finishes our notes on limits. Woo! So we got 14 minutes left. So we can cover any questions you have on the previous problems, anything like that. Let us know. Even homework questions.
All the questions.
Give us all the questions.
You want to help me with chemistry?
Nope.